After watching this video lecture, students are going to be able to identify the difference between cations and anions and write electronic configurations for those ions. So up until now, we have been looking at atoms on the periodic table as being neutral, meaning that the number of protons and the number of electrons are equal to one another, and so no overall charge is present. Now, cations and anions are actually examples where that's not true. So a cation, cations form when atoms have lost electrons. Okay, and so cations form when atoms lose electrons, and the number of protons that you have is greater than the number of electrons. So cations are going to be positively charged. Okay, so like, sodium, copper, okay, ions. There's lots of different examples. Okay, and anions, form when atoms gain electrons. Okay, so the number of protons is going to be less than the number of electrons. They're going to be negatively charged. Okay, and examples are like fluoride, ion, okay, oxygen, anion, okay, and what have you. Okay, so cations and anions are both charged versions of the various atoms. Now, the driving force behind why all of these atoms form cations or anions is the fact that they want to gain more stability, and they want to be like their nearest noble gas. So this driving force, this desire to have more stability, is going to be what causes the cations and anions to form. Now, whether you form a cation or anion is going to be dictated by your proximity to your nearest noble gas. So if we go ahead and we look at period 2 here, obviously elements on the right side or further to the right of this period are going to be closer to neon, and those further to the left are going to be closer to helium. Okay, and so depending on that proximity, that's going to dictate whether electrons are gained or lost. So if we look at fluorine here, fluorine, okay, is right next to neon. Okay, neon has a completely full shell. It has 6 electrons in that p orbital, while fluorine only has 5. Okay, so in order to be like neon, fluorine's going to pick up an electron, okay, and it's going to form a -1 charge. And if you look down the group here, okay, similar characteristics or similar behavior is going to happen with the elements below. Okay, so those halogens are going to behave similarly when they form ions, and in that case, they're going to form anions, -1 charged anions. Okay, in the case of oxygen, it's 2 away from neon, so we're going to have a -2. Okay, same thing down the group. Okay, it's going to follow those characteristics. Nitrogen is 3 away. Okay, so it'll gain 3 electrons to be like neon. Okay, now when we get to carbon, what I want you to notice is carbon is 4 spaces away, or 4 electrons away from being like neon. It's also 4 spaces away from being like helium. So in the case of carbon, carbon could go any direction. It could be +4 or -4. And this is very important when you look at organic chemistry because carbon's flexibility allows it to be a very active and diversely bonded atom in structures. Okay. Now, when we get to boron, what I want you to notice is all of a sudden we're 5 away from neon and 3 away from helium. So at this point, it's more favorable or less energetically taxing to lose electrons. So in the case of boron, boron's going to lose 3 electrons, okay, and form a +3 ion. Okay, continue with beryllium. Obviously, beryllium is also closer to helium. It's going to lose 2 to be like helium, +2. Okay, and then when we get to lithium, okay, it's 1 away, so it's going to lose 1 electron to be like its nearest noble gas, which is helium. Okay, and so basically these characteristics, again, are going to follow down the group in terms of behavior when forming cations and anions. Okay, and so the periodic table will get you to where you need. So when we are discussing our +1 or -1 charged cations and anions, what I need you guys to be able to think through in terms of how I'm determining the plus and minus charges is this relationship here between protons and electrons. So remember, atoms always have the same number of protons. That's what identifies them as their specific element. Okay, now by altering the number of electrons, you're altering the balance between the charges. Okay, so over here on the right-hand side of the table, when I pick up electrons, what I'm doing is I'm making it so I have more electrons than protons. Electrons are negatively charged. The more negative charged things I have, right, the more negative my charge of my ion is going to be. Okay, conversely, okay, when I lose electrons, when I'm forming cations, the number of protons remains the same, okay, but my number of electrons decreases. So what ends up happening is that there are more positively charged subatomic particles in that ion, and it subsequently has a positive charge. Okay, so make sure you think through that and that you're comfortable with it. People have a tendency to make the mistake of looking, hey, to the right, I am adding electrons, so I should be plus something. Remember, you are adding a negatively charged species, so you are going to become more negative. It's a very important point. Take the couple minutes to get that straightened away in your head. Okay, now let's go ahead and let's talk about electron configurations with cation and anionic species. Okay, so if we go ahead and we look at, let's say, sodium. Okay, sodium's electron configuration, 1s2, 2s2, 2p6, 3s1 is going to be the electron configuration for the neutral atom sodium. Okay, but the cation, right, has had an electron removed. Okay, so for the cation, the electron configuration is going to be as follows, right? And that's going to match up with the previous noble gas, which is neon. Okay, in that same thought process or that same approach, if we look at fluorine's electron configuration, 1s2, 2s2, 2p5, this is the electron configuration for fluorine. Okay, the fluoride ion, okay, we have 1s2, 2s2, 2p6. Okay, it has an additional electron, which is why it has the -1 charge, and you subsequently end up with your fluoride ion. Okay, so this is electron configurations for anions and cations of main group metals, or main group elements, rather. Okay, but I also want to show you something when talking about transition metals. So there's a little bit of difference there, and I want you guys to see this. Okay, so transition metals, something really weird happens. Okay, so when we remove our electron here from the sodium atom to form the sodium ion, okay, we removed from the 3s1, we've removed from whatever was at the end of our electron configuration. Okay, and that works really well for main group elements. However, when we talk about transition elements, you always need to remove s electrons, or electrons residing in the s orbital before d's. Okay, and the reason why is because basically as we get further and further away from the nucleus, we start including d orbitals, there starts to be very, very small differences in the energy levels of the s's and the d's. And what ends up happening is that the s orbitals end up being slightly further away from the nucleus, and subsequently are going to be where we remove our electrons first. So if we go ahead and we look at like an example, so like chromium. Okay, if we go ahead and write the noble gas electron configuration for chromium, we're going to end up with argon, and then 4s2, 3d, 1, 2, 3, 4, 3d4. Okay, and this is just the shorthand version, right? This is the noble gas. So let's say we had chromium +1, okay, as the ion that we were forming. Okay, so in that case, remembering this rule for transition metals, that we remove our our electrons in the s orbital before the ones in the d's, we would end up with the following. Okay, so you notice that? Okay, I've removed the electron from the 4s orbital instead of the 3d, and we would continue if I had chromium +2. I would remove the electron again from the 4s. Okay, we would have this. And then if we continued to remove electrons, eventually I would start pulling them from the Ds. Okay, and so remember, guys, for your transition metals, you're going to remove your s electrons before your Ds.